Okay, in this video segment, what we're going to do is hit a couple of the different laws of thermodynamics and introduce ourselves to the mCAT equation, which allows us to measure energy change across the temperature range. So, to start off, we want to talk about the Zeroth Law of thermodynamics. Basically, what the Zeroth Law does for us is allows us to correlate equal temperature across different substances. So, what the law technically says is if you have A and C at thermal equilibrium, and C and B are at thermal equilibrium, then by rule, A and B must also be at that same thermal equilibrium. Now, thermal equilibrium is just kind of a fancy way of saying equal temperature. So what we're really saying here is that if A, C, and B are all at equilibrium, they're all the same temperature, is what the law is telling us. This is going to help us out as we move forward in this unit, as we start dealing with thermometers in water, ice next to other ice, water next to ice, metals next to water, that kind of stuff. Just this concept that if you put two things together, if they're the same temperature, that means they have the same thermal equilibrium. That's what we're talking about. Now, the second law of thermodynamics, we're going to watch a little slideshow first. Okay, so this is not the entire second law of thermodynamics. It is just a portion of it that deals with heat flow. And basically what we're saying is that if you take two objects that are different temperatures, put them together, we have a flow of energy always from hot to cold. So there is no such thing as cold flowing into hot. It's all about energy flowing from the hot object into the cool object. Now that energy flow will continue to happen until they reach thermal equilibrium, or until their temperatures are the same. It doesn't mean that both objects have the same amount of heat energy, because remember, heat energy is about the total mass of the system involved. It really is only about the equal temperature between the two substances. We can use that to kind of start talking about what happens if we start putting two things together. So, exploration number one. If we have 50 grams of water at 100 degrees Celsius with 50 grams of water at 20 degrees Celsius, if I mix the two together, what should the overall endpoint be? Okay, so assuming we have distilled water and we have 50 grams of each, 100 degrees, 20 degrees, the midway point between those two things is 60. So most students answer, hey, this is 60, and they're pretty confident with that, which would make sense according to the Zeroth Law and the second law of thermodynamics. However, if we go on to the next exploration, where we now have a difference, people start to have a little bit more lack of confidence, we'll say, in terms of what happens. So in this scenario, we have 50 grams of water at 100 degrees Celsius with 25 grams of water at 20 degrees Celsius. So again, our temperature difference is the same. We're still using water in both cases, but now we have unequal amounts of water. So to figure this one out, again, you had to factor in that the masses are different, because mass plays a role in these calculations that we're going to be doing in a minute here. So mathematically speaking, what we see here, our total mass of water is 75 grams, and 25 grams contributes a third of that, and 50 grams contributes 2/3 of that. So if you're going to do the math, you have to factor it in that way. Now there's going to be an easier way to do the actual equations and calculations in a future video segment, but for now it's just realizing that because the 25 grams of water is less than the 50, that we won't get 60 anymore. Instead, we're going to get some number that's higher than 60, but still definitely below 100, okay, as we do this, because less mass of the cooler substance should mean that the overall temperature at the end is higher than if they were equal mass. In exploration 3, now what you see is that we have 50 grams of zinc and 50 grams of water. So in this scenario, our masses are the same. We still have a temperature difference, so we will need to get to some equilibrium. But now because we have zinc versus water, that throws a whole nother factor in here. We talk about, does it matter if it's zinc or water? Or will our number still come out to be 60 like we initially said in exploration number 1? And the reality, because zinc and water deal with heat energy differently, we will have a different number here. Okay, and it's going to take us until we get to our calorimetry experiment, into this concept of calorimetry, before we actually can mathematically solve this. But again, in the exploration, it's just this idea that the substance that we have actually plays a role in how we can calculate heat energy changes. So if we combine those three things together, and we talk about what are the variables that determine our heat change, we have three things: the mass of the substance, starting and ending temperatures, and the type of substance. Now, with the type of substance, we need to introduce a new term, and that new term is specific heat capacity. Okay, so our specific heat capacity is basically the capacity of something to absorb energy and then release it back. Okay, every substance has their own specific heat capacity. Some substances have really small ones, some are very large, and then the difference between those two numbers determines how well something absorbs energy and how much it can absorb without changing temperature, and then how much energy it is able to dump back out when it does change temperature. So if we define specific heat capacity, it's the amount of energy needed to raise 1 gram of a substance 1 degree Celsius. So if you imagine, if you have a high specific heat capacity, it takes a lot of energy to raise temperature. If you have a low specific heat capacity, it doesn't take much energy to raise its temperature. Here we see a chart of the different specific heat capacities for several of our elements and some compounds that are pretty common that we use in a lab setting. One thing we want to do is take a look that most of these are in the decimal range, but if you go down to ethanol and things like water, we see that they have a really high specific heat capacity. Now, let's do kind of some mental comparisons here. So let's just use water compared to tungsten because they're right next to each other in our little table here. For water, it takes a lot of energy to warm it up because for every degree Celsius you want to warm it up, it's going to take 4.18 joules of energy. Now for tungsten, for every degree Celsius that you're going to warm it up, it only takes 0.132 joules of energy. So we see that it takes a lot more energy to warm up water because it has a high specific heat capacity, whereas it takes less energy to warm up tungsten. Which means if we actually gave them both the same energy and they had the same mass, that the tungsten would heat up much faster and to a much hotter temperature. However, if we raised them both to the same temperature, it would take a lot more energy to get water to go that way. Okay? So when you're dealing with specific heat capacity, you really have to think of it as basically this ability to absorb energy and not change temperature. So the bigger the number, the better it is ability to absorb energy and not change the temperature. Now, if you flip the coin and you do have something like water or ethanol that have high specific heat capacities, and they do change their temperature a lot, okay? If it goes up, it means it takes a lot of energy to do that. However, if their temperature goes down, because they have high specific heat capacities, that means they have a lot of energy to give away. So things like water, where if you reduce its temperature, it can dump a lot of energy into the surroundings and warm other things up. That's one of the reasons why water is so good for cooking and for heating, because once you heat it up, it has a lot of energy it can have to store. Now, when we calculate heat changes, we had to use what we call the mCAT equation that combines all these variables together. A new symbol for us is Q. Q stands for energy change, which is in joules. M is our mass, which we do in grams, and delta T, our Greek letter delta, which stands for change, for temperature. It's your temperature. Little f stands for final, little I stands for initial. So you have your final temperature minus your initial temperature. It can be in degrees Celsius or kelvins, it doesn't matter which one. And then C is our specific heat capacity, again in joules per gram degree Celsius, or joules per gram Kelvin if you're using Kelvin temperature scale. Either scale works because we're dealing with a change in temperature and not an actual absolute temperature here. Okay? We usually call this equation mCAT because it kind of looks like the word mCAT there. And it allows us to calculate energy change anytime we change temperature. So let's go through a little practice problem. What is the energy change for water when 50 grams of it goes from 100 degrees Celsius to 60 degrees Celsius? Okay, so if we set this thing up, we know that our energy change is mass times Celsius, specific heat capacity times our change in temperature. And we want to know what the energy change is, so we're actually solving for Q. So in this case, the mass that we have is 50 grams. Our specific heat capacity for water is 4.18 joules per gram times degrees Celsius. And our change in temperature is going to be our final minus our temperature initial. So our final temperature here is 60 degrees Celsius. minus the 100 for our temperature change, okay? So if we do this math, we get 60 minus 100. Now that's a negative 40 degrees Celsius times the 4.18 joules per gram degrees Celsius times the 50 grams. And we notice that grams and Celsius cancels, so we're left with joules, because Q is labeled in energy or labeled in joules. If we plug these numbers in, we will see that as the temperature goes down, energy had to be released for those 50 grams. So as a result, we end up getting a negative, because we end up with a negative sign, 8,360 joules of energy to make this process happen. That negative sign is definitely needed here because it represents that energy is being lost by the water, that the water is not gaining but losing that energy. Okay? I want to have you guys go ahead and practice this one on your own, and then we'll show you the answer key here in a second. So in this case, we're dealing with 4 liters of water at 10 degrees Celsius, and we're going to heat that water using the energy from a regular sized Snickers bar. Now that energy is 273 calories, capital C calories. So what you want to do is calculate the final temperature of the water after heating. Okay? Your conversions for calories and joules are here. You're in liters of water, so you have to convert that to grams before you can do your math, and then you can solve. So go ahead and solve that now and pause the video, and then when you have an answer, go ahead and unpause it and let's see what the answer key is. Okay, so if we pull up our information, we had 273 calories. We're going to convert calories to scientific calories, and then we're going to convert to 4.18 joules. That should be a lowercase c, sorry. Which tells us we have a lot of joules of energy here. We know the density of water is 1, so if we take that density times 4 liters or 4,000 milliliters, we get 4,000 grams. Okay, so we convert it to grams. Now we plug into our equation, but we're solving for temperature final, so we got to rearrange it a little bit to solve for temperature final. If we rearrange and solve, we end up getting 78.3 degrees Celsius. Now, if you got 68.3, what you did is you solved for the change in temperature, you solved for delta T, you didn't actually solve for the final temperature, so you didn't factor in the 10 degrees that was already there when the process started. Okay? We're going to end the video here. Our next segment is going to go into the first law of thermodynamics and what happens when we have to deal with 2 things changing temperature at the same time. Thank you.